All right, so what we're going to be talking about today is choosing a camera for astrophotography. So I subtitled this, Sorting Good Photons from Bad. Al originally asked me to do a talk on digital SLRs versus CCDs, so we're going to use that as kind of a test case and an example for trying to look at what is going to make a good camera for astrophotography. Just to give you a little bit of overview here, we're going to start off talking about really what are the criteria, what is going to end up making what we're going to call a good camera. And we're going to then slide into a discussion of signal to noise and a signal to noise ratio. So what is signal to noise and where in the image does it actually matter? Because a lot of people use the term, there are a couple different ways you can think about it, and I'll be talking about one in particular. So then in terms of a digital SLR versus CCD kind of thing, I'm going to show you a number of image comparisons and then try to hammer home what it is about a digital SLR. They have some great pluses to them, but it is going to be tougher to go really deep with them. So why? If you don't know me and know my stuff, one of the things that I've been doing over the years is I've done a number of camera reviews. And since I write software for cameras, I get a lot of cameras to come my way. On cloudy nights, my SIG line says, and too many cameras to mention. Well, I actually went through and counted them up a couple nights ago. Right now I have 25 cameras at home. It's a lot of cameras. I mean, sadly, almost all of these, one of my good buddies, Michael, gives me a hard time all the time because most of these, the most interesting thing that they've taken a picture of is the bookshelf across the room. All right, it's kind of sad, but just to give you an idea as to what I have worked with here, when I'm talking about digital SLRs, I'm going to be talking almost entirely about Canon digital SLRs because those are the ones that I've had the most experience with. They are the ones that are most popular in astrophotography for a few reasons. But these are ones that I've had on the test bench, my own 350 XT that was filter modified, the 40D, XSI, 50D, 5D Mark II, and I've got a Nikon around as well now. Number of different ATICs, pretty much all the Meads, a couple of SBIGs, a couple of Kevin's QSIs, a lot of the QHYs, a couple of Starlight Expresses, the Fishcamp Starfish, Optic Stars. There are now a couple more on the way to me as well. So I've been looking at a number of different cameras, looking at them on a test bench, and looking at some number of them actually under the stars as well. A couple of them actually get out. But I just wanted to give you an idea as to, okay, now here's the sort of space that I've been working in as I've been looking at these. But now when we say, okay, what's going to make a good camera for astrophotography? Of course, you're going to have a bunch of different criteria, and each of us are going to have different criteria. So I don't want to come out in all of this and end up saying things like, oh, well, this is the one and only good camera. No. Each of us is going to have to trade off and weigh a number of different criteria and factors when making our decision. So how much does it cost? For some of us, well, that's a very big thing. For some of us, and feel free to buy me gear and donate it, it's not such a huge thing. Don't buy cameras, I got a lot of those. But okay, so ease of use. I mean, can you even get the camera? Also, how easy is it to use? I mean, if you were to be doing something like taking a rig in a backpack and hiking up a mountain and doing something, you're going to want something that's a much more minimalist kind of setup. And it darn well better be pretty darn easy to use. Extra functionality. If you're going to be able to, if you want to do something like take vacation shots, as much as I love Kevin's cameras, a QSI 540 is not what you want to take with you as you go and take vacations. Like, okay, kids, stay very still while I get the tripod and the laptop set up, and it's got to be color. I know, honeys. Let me get the filter wheel going and take 3 separate pictures. Don't move. All right. So if you are going to be in, if you're going to end up saying something like, oh, look, hey, I need a new camera for astrophotography, and well, geez, I can kind of pitch this as it'd be great for that trip that we're going to take. All right, that's going to push you in a direction that if you're getting something solely for astrophotography, we probably wouldn't push you. Let's say you want to be able to do something like lunar and planetary shots as well. Again, there are trade-offs here that'll push you more toward one kind of camera or another. So there are extra functionality bits that come into play. Sensor size and pixel size. What kind of shots do you like taking? Do you love those little tiny planetary nebulae and cataloging every single one of them you possibly can? All right, if you do, a huge chip isn't going to be a big deal for you. If you're a sucker for those big wide field panoramas, give me that big chip, because otherwise you're taking 87 different things in a montage and trying to come up with some shot there. What we're going to be talking about today, though, are things that I can actually kind of quantify and that will be able to cut across a lot of these different kinds of criteria that you may have. So this is the quality of low light, long exposure images, because I'm going to be talking about DSO imaging and all of this. All right, so we're going to be starting off in the beginning here, talking about signal to noise ratio, and realizing that when you are taking an image, your goal is to estimate the intensity of this target relative to the background sky. So you've got some arm of some galaxy, some cool wispy bit of some nebula, and what you are trying to do is say, all right, the intensity of this is X, and the intensity of the background or this dust lane or something like this is Y. And that is how you're making up your image. Throughout all of this, at each pixel, you are just trying to say, how bright is it? And you're trying to get as clean an estimate of it as you can, because that is how you're going to build up your image. The quality of that estimate is determined by the signal-to-noise ratio. So we're going to spend some time stepping through this. If you have a nice high signal-to-noise ratio, you're going to be able to see that arm, you're going to be able to distinguish it from the background, and it's going to look like a nice, smooth image. If you have a very low signal-to-noise ratio, you're going to miss that galaxy arm, or it's going to look very, very noisy. One of the things that we're going to hit in some of this, I've come up with a CCD camera simulator. And I'm going to use this simulator to generate a number of images that we're going to look at. This is going to be nice and clean from any particularities of the seeing, of my sight, of a camera, et cetera, but it does help then to make some points on signal to noise. And so I factored in a whole bunch of things into a MATLAB model. I used a 9-hour image at 0.2 arc seconds a pixel from Hubble, so it's basically a perfect image. I went through and said, okay, let's model the seeing, let's model the QE and the exposure duration, add in sky glow, resample onto a detector, dark current, shot noise, read noise, quantization error, et cetera. What this lets me do is this lets me take something and say, okay, here is a simulation of M51 from urban skies. Fixed telescope, here I'm doing things like my image scale is 1.5 arc seconds a pixel. There's a Gaussian blur of 2 arc seconds worth of full width half max, et cetera. And I can say things like, what does a camera's QE do to the signal to noise in my image? So here we have a perfect camera with a QE of 1. It's got a read noise of 8 electrons, so there's some noise in here. And there's also noise in here because of the sky glow, the shot noise. And we can see, obviously, if I were to choose which one of these 3 cameras would I pick, well, you go and you pick the QE of 1. QE, quantum efficiency here, is going to end up basically equaling aperture when it comes to signal to noise. So we can take a look at things like this, and we can say this is what it looks like in urban conditions. What does it look like in a more rural condition? Oh, well, that's a much better image overall. You still see, of course, there are differences. If I get to pick this camera versus this camera, well, I know which one I'm going to grab off the shelf, and I get 25 of them, so I can hopefully pick one closer to this. So, okay, I can see this. Now, you'll notice also, though, that in terms of sort of the steps worth of signal to noise here, this may not be a perfectly even kind of scale, because there are other things that are going to go into our signal to noise in our image other than just the QE. There's another thing, hopefully, you can get from this. If you compare this image to this one, what would you rather have? A QE of 4 camera from a rural site or a QE of 1 camera from an urban site? Well, I know which one I would rather have as my raw data. Give me the mediocre camera in the dark sky site in this kind of simulation any day. So one of the things then that's going to come out of this here is that the camera is only going to be able to do so much for you. And your local conditions are, can end up dominating the noise term and therefore the signal to noise ratio. And so things like the quality of noise, the kind of noise that you have in there is going to dictate how this comes out. But it also then does show, okay, look, if you're trying to build up some nice clean image and you got this, you are going to have a much tougher time doing it than if somebody else has this. All right, so this is where signal to noise is going to come in. So let's define signal to noise mathematically here. It's just the ratio of the signal to the noise. We're not always all that creative when we come up with terms. So signal to noise ratio is the ratio of the signal to the noise. All right, so signal in this equation here, signal comes photons from our DSO, but also photons from sky glow and photons from dark current. So in your classic signal to noise, all of this is signal. Now, Each of these things has a noise component associated with it as well. Shot noise, anytime you read off anytime the photons are coming in here, there's a noise associated with it. They don't come in some perfect stream. That's not the way photons work. And so we have shot noise. So anytime there is signal, there is a shot noise component that goes along with it. There's also this thing, read noise. Anytime you read off the sensor, you have noise that is injected into the image as well. And again, remember, our goal here is to estimate the intensity of the target relative to the background sky. All right, so what's going to make for a good camera, good performance in this kind of thing? Well, it's a signal-to-noise ratio, and we want that to be as good as possible. So we can do things like we could drop the noise. If you have lower read noise, you are going to have higher signal-to-noise. If you have lower dark current, you are going to have higher signal-to-noise. Yes, with dark frames, you can subtract out the expected value on average what that dark current should be, but there is shot noise associated with it. And that shot noise you're not going to get out by dark subtraction. So if you have a lower dark current or you have lower sky glow, which of course isn't going to be your camera's fault. Your camera can't know whether you're sitting next to LA or you're in New Mexico skies there. So this is going to end up making us better. Also, if the noise is cleaner. In a good amount of the talk here, I'll be talking about noise as if noise is noise is noise. And that's not true. Some cameras have patterns to the noise that draw our eye, which then make it so it's going to make a less pleasing kind of image. You can drop the noise. You can also boost the signal. You want a higher signal-to-noise image? Get more signal. So have bigger aperture. You're getting more photons that you're getting down onto that CCD chip. Have higher quantum efficiency. You're converting more of those photons into electrons. Have not just a higher sort of peak QE, but have a nice big broad QE. So you're getting all sorts of different colors of photons hammered down onto your chip. Have bright targets. Yeah, you laugh, but look, it's true. If you want to get a higher signal-to-noise image, start with a brighter target, and you're going to have an easier time, actually, of this. Again, that's not the camera's fault. Let's step through the math here a little bit more, just to try to unpack this. Our signal is going to be the duration times the total flux. Flux is just the rate of photons that you have coming in here. So you may have 100 photons a second coming in. If you have 100 photons a second in 1 second, you have 100 photons on average. If you have 10 seconds, you have 1,000, etc. Total flux here, well, flux is going to be coming from a bunch of different sources. We have photons coming from our actual target. We have photons coming from the sky. And we have, well, basically photons coming from the dark current as well. So this is going to be our total signal, but we really only care about one of these. We really only care about the target flux. I have no desire to have a perfect image of my sky glow. That's not the goal. The goal is to have, of course, the perfect image of my target. So that's the signal that we're actually really going to be caring about here. So we're going to take this equation here, and we're going to end up saying then that one take-home message from this is that longer exposures is going to mean more signal. And more flux, a brighter target, a bigger scope, a higher QE is going to equal more signal as well. So that's one way we're going to be able to boost this equation. Noise. Shot noise, I mentioned before. Anytime you're getting signal, you're going to be getting shot noise associated with it as well. And it's the square root of that signal. So our shot noise is square root of our total signal from our target, our sky glow, and our dark. Total noise, the way noise adds here, we've got to sort of stick it together like this, is the square root of the total signal plus the read noise squared. All right, doing all of this just to get down to a basic sort of setup here, our target signal-to-noise ratio. This is what we actually care about. Again, I don't care about making a pretty picture of my sky glow. I want to know, in this arm of M51, how well am I getting it? So you have the target signal, the signal just coming from M51's arm there, over this noise term here. Square root of the total signal and the read noise. So this is what we want to have be as high as possible. Boosting this up or dropping this down. Now, a couple of things I've tossed, by the way, into the presentation here are really just here for your notes afterwards. These are a little bit more text-heavy slides than I often do, and things like this I stuck in, and unfortunately the version of this that is in your handout has the wrong equation. It flipped these two. You'll get a negative signal-to-noise ratio if you actually follow the one in your handout. fix this here, because if you want to go through, I wrote an article for Cloudy Nights on actually measuring this in a spreadsheet for using it. But if you want to take something like, I'm going to sample an image of mine and I want to calculate the signal to noise, you can say things like, how bright is it in the DSO minus how bright is some background. That is my target signal. And then over the, here, this is going to give you the shot noise and the read noise there. All you need to do, as I say, is flip those two terms. All right, so I've thrown a number of equations at you. These aren't big, tough equations, so you're either sitting here yawning or you're saying, oh my gosh, math. I thought I could forget that. Couple of take-home points for us here. Cameras aren't going to make brighter targets or darker skies, but both of those are significantly going to influence your signal-to-noise ratio. Cameras aren't going to be the absolute cure-all to everything here. Sensitivity of the camera is going to help. Doubling the QE, however, is not going to double your signal-to-noise because you have various other things going in there. You've doubled that QE, and so you're now getting, well, twice as many photons from that sky glow as well. You still have the same read noise. There are other things that are going to be going into this here as well. Urban skies, we're going to end up seeing things like shot noise from the sky glow is going to dominate. It's going to be a huge noise component. I tried to sort of show that a little bit in that comparison of M51. Read noise will end up probably going away if you take any moderate length exposure. The quality of that read noise still is going to end up being a factor, and we're going to hit that in some of the Canon shots. So if you're trying to evaluate cameras, you either have to do things like nice simulations or controlled environments, or do things like if you're under a very dark sky, you're going to be able to see the true nature of the camera. Well, often you'll be able to see that sooner or cleaner if you have very dark skies. And again, there's going to be no solution for darkening your background skies. Urban skies, signal to noise is almost always going to be poor. So one way to think about it might be saying, well, look, I'm in urban skies, I can use anything. I can take my old Philips Vesta, 690 webcam here and aim it up there, and because everything is shot noise, it's not going to matter whether I use that or whether I use a nice cooled Astro CCD. Well, no, that's not going to be the case either. For one thing, the kind of noise, the quality of the noise and that sort of thing, your signal to noise poor, which means that you are going to be stretching the bejesus out of this image to try to get anything. It's like, I think there's a galaxy in there. Somebody told me M31 is supposed to be in this region, and I really at least want to see it from my backyard here. All right, so you're still going to be stretching it like crazy, which means then you're going to be getting down deep into the noise in your image. And it darn well better be a sort of clean noise that you can work with and pull things out of. Okay, so given a bit of an overview, hopefully, of signal-to-noise ratio here, now what's up next? Some image comparisons. Over the years, doing things like tests and reviews for Al's magazine, I've had a chance to be able to have side-by-side a number of different camera rigs and be able to say, all right, what do we actually get if I stick camera X, Y, and Z, shoot the same target at the same time? What do the images actually look like? So I'm going to give 4 different examples here. One, urban skies, M51, with this is sort of a quote back in the day, a couple years ago, a modified Canon Rebel XT, DSi-2 Pro, ATIC 16 IC, and Starlight Express. If you notice, you may think I'm cheating here. These are all monochrome cameras, and this is a one-shot color, of course. But that's going to be something we're going to hit here. What do having color filters on your chip actually do for you in terms of signal to noise? You can choose for dedicated Astro CCDs to go the monochrome route. You can't choose that for digital SLRs. There are no monochrome digital SLRs out there. I'm going to show you some indoor target tests. So set a camera up on a tripod, aim at a target across the room, because really photons from outer space versus photons from inside my room, they're photons. And my camera doesn't really know the difference. So we can have some more controlled tests indoors. Couple, again, these are all one-shot color sort of setups comparing that same Canon Rebel, but also a 40D now. Here now some indoor targets on comparing across 3 different Canons, and rework of redoing of some urban M51, some new data here from, again, a Canon XSI, a QHY8, a QSI 540, and a DSi 3C. Now remember what I said though before was that, all right, if you go and you're shooting under urban skies, your shot noise is going to really dominate. And you're going to have a tougher time seeing the difference between cameras. you should be able to pull them apart and really see the true nature of the camera better under dark skies. Well, I don't live under dark skies, and so when I'm trying to do things like take nice test shots like this, you get urban sky conditions. That said, we can see differences across these cameras here. Here we've got a Me DSi-3 Pro, a Starlight Express M7, an ATIC, and a Canon 350 XT. Now, in terms of which one of these is best, all right, well, we can talk about which one is best. We can also just end up saying that, well, the Canon is clearly pulling up the rear here. All right, well, it's unfair. Come on, here you're getting color data, and here these are monochrome bits of data. All right, yeah, you can call this unfair. Oh, thank you. I think probably with that one we should be pretty good, because I don't want everybody falling asleep in here. We see a pretty good large gap here. This is a stack of the 5 best frames. These are 1-minute shots apiece, so we're not letting thermal noise dominate too much in all of this. So one thing that you could say is, okay, look, you're using monochrome cameras. Come on, that's unfair. But, as I say, you get to choose monochrome if you want with a dedicated Astro CCD. In all of this, when I'm talking about the signal to noise of the image, and I'm going to give you a demonstration of this, it's the signal to noise of the luminance that you really care about. That's what's going to be able to show you, is there a galaxy arm? Is there a dust lane here? Yes or no? And what does it really look like? The color data can sort of shine through. And with monochrome cameras here, you can pick up a whole heck of a lot of luminance. So call me a cheater or say it's a practical kind of thing. Let's go through some more data here to see if that still holds up, whether it all comes down to the one-shot colorness. This is an indoor short exposure shot. Simple test shot here. I have the word text getting dimmer and dimmer and dimmer across. And we also have just this sort of generic target here. And we see that, all right, S-Big, Canon, QHY8, these are all looking pretty darn similar. All right, well, they're all one-shot color sort of cameras, and so maybe this is what's going on here. It's not going to be the whole story by far. There are differences between these shots, but right now, well, okay, look, this thing here cost like $500 at the time, and it's got a huge chip. This thing here was like, $1,700, $2,000 at the time. Whoa, okay, this is looking pretty darn good. We see differences. They're not huge. One thing I do want you to start paying attention to, can you start to pick out some streaks in this image? These are actually, believe it or not, horizontal streaks. I know I'm going like this, but the image is rotated 90 degrees because that's how I happen to have the camera set up. But you'll see that there are some streaks in here, and that's going to come up a little bit later. Here, however, is the same kind of setup, exact same time, but instead of taking a 1-second exposure, I've now cut the light down drastically, and I'm taking a 5-minute exposure. Now you get to see the ST2000 and the QHY8 shine. Don't mean it literally, not this little sort of glow here. This is actual reflection. But you get to see, okay, look, we're easily getting text 6 out here. Yeah, no. No, and here you're even getting text 7. All right, there's a heck of a lot more noise in these images than this one. In a 1-second exposure, you don't have time for thermal noise to become anything. In a 5-minute exposure, you do. And so the cameras that have cooling and good deep cooling on both of these cameras here don't have real appreciable dark current. This is what the dark current is doing to your image, because I go back when there's not dark current, everybody looks the same. Here they decidedly don't. All right, so what we're starting to see now is that as you start to have things like thermal current become an issue, you can start to see these pull apart. And there are good physics reasons why we should see that. How about, okay, look, I've been showing you so far things like a Canon Rebel XT. What happens as we look across a range of digital SLRs? So I had the privilege of being able to have 3 different Canons available for test at the same time. This is a 30-second image, again, one of these indoor test shots. Now these are oriented properly, so you see the horizontal streaks are actually horizontal. You see them here on the XSI and the 50D. You don't see them nearly as much on the 5D Mark II. And you take a look in here, I mean, it looks like some regions like this. Compare it to this. Compare it to this. All right, it's clear that the 5D Mark II is certainly doing better than the XSI. The difference between these two in terms of the signal to noise in the image or in terms of what we can resolve, it's smaller. There is a difference here. But you certainly do have more of this kind of noise on the 50D than you do on the 5D Mark II. I do want to point out the 5D Mark II, it's not exactly an inexpensive camera here. $2,700 I just checked right now at B&H Photo for the body only. You've kind of lost the argument of, okay, look, it's, inexpensive solution, but you certainly are doing a bit better. I would argue that the difference isn't incredibly dramatic. It's not like the difference that we're seeing on something like this. But there's a difference. Urban M51 Redux here went out and took shots using a Canon Rebel XSI, QHY8, QSI 540. Just take a look at these here first. And we see again, okay, look, these are both one-shot color cameras. Okay, yeah, some of the Canons do a little bit better than the XSI here, most certainly. This is already, though, a pretty decent difference between them here. So this is a 3-minute frame, and so again, we're getting things like dark current to become an appreciable component, and the shot noise associated with this dark current to be an appreciable kind of thing here. We're also going to end up seeing that the sensor QE is not going to end up being quite as good even as something like the QHY8. Those two are conspiring to give us, well, a lower signal-to-noise image. What this means is that I'm going to end up having to work a lot harder and get a lot more data to get this to end up looking like a nice clean shot of M51. It's not going to be impossible. It just means I'm going to have to take more data to overcome that signal-to-noise. Because remember, all right, I've got more noise, so it just means I need more signal. I need to do things like have longer exposures or have more exposures. By the way, it doesn't necessarily, follow that, okay, look, 3 minutes is great, and so 5 minutes is, phenomenal, and if I could get a 50-minute single subframe, that would be fantastic. It's really going to come down, by the way, to just the total amount of time you have, and past a point where you cut the subframe really isn't going to matter too much. So, okay, here we do also get to see that, okay, yes, obviously if I stick a green filter or a red or whatever filter over, over the sensor, I'm going to get a hit versus getting the luminance data, but in some ways that's kind of the point. That is one of the things that a dedicated Astro CCD is going to do for you. It's going to let you get this kind of luminance data, which is going to make your picture look pretty, and then you can have a color overlay to go in there as well. So color filters are going to be some source of the loss, but there still is a pretty good gap between the digital SLR and the CCD. Now, okay, some of this I've been showing things. It's not like it's not like Kevin's 540 there is an inexpensive camera. This is actually my personal camera. I bought it with my own cash, so that's one of the 25 there, one that I did buy. It's a very good camera. But in any case, here, I'm saying, okay, look, here's the Canon, here's a Meade DSi 3C. Ignore the dust motes. Apparently, I wasn't taking very good care of my DSi 3C sensor at the time. But again, you see that, okay, look, there's a big difference here in terms of the signal to noise on those images. All right, we're going to come down to why. Why is it that it's tough to go very deep with digital SLRs? All right, going to hit a couple points here. One-shot color sensor is going to end up hurting you in terms of the luminance signal to noise. Sorry, it's going to. You've stuck a color filter over there, and so you're cutting your light by at least 66% hitting each thing. So your signal is going to be down. You're trading it a whole bunch of convenience. I've done a lot with one-shot color cameras. I do like them, but you do have to keep this in mind. The relatively low QE of the sensors to begin with is going to be a part of it. It has very, very good read noise, but there are thermal issues that we'll talk about. There's also some internal scaling of the images and internal processing of the images that ends up being limiting the effectiveness of your dark frames. And there's also some fixed frequency variable location noise, some structured pattern noise that's going to be a bit of a problem. So first, some number of you have done LRGB. How many people, folks, have done LRGB style imaging? Okay, almost everybody here. I'll then go through this quickly. Eye is very sensitive to changes in luminance. That's kind of what we do. Chrominance, much less so. If we have a good high signal-to-noise luminance, we'll be in great shape. So here I've taken a shot from the Hubble. This is the RGB data. This is just the luminance data. So we can split this out. This really isn't chrominance. It's really just a straight RGB. Here's the slick thing that we can do. We can take this RGB, and I can blur the bejesus out of it. technical term here. Warren always gives me a hard time for the technical terms. This is blurring what, this is actually 4 bejesuses, this is 2, and this is 1 bejesus. So, okay, we can do this kind of thing. So if I've taken, you know, bin data or I have very little data, we know one way you can get rid of noise, blur the bejesus out of it, or at least 4 bejesuses, and you've gotten rid of a whole bunch of noise. All right, but this looks like crud. You're not going to stick this up on your web page because it looks like crud. However, if you have a luminance thing that you stick on top of that there, even the 4 bejesus one looks pretty darn good. Yes, you've lost a bit of saturation, so you can do some things to bring back that saturation, but you can do that. Here's why LRGB works. If you take a straight RGB image, I'm just going to have a hypothetical set of numbers here. Let's say I have 600 seconds to image. I can divide that among my red, my green, and my blue evenly here, RGB set up here. And my filters, well, look, I've got filters on each one of these images here, each one of these sensors. And so I'm only going to get about 30% of the photons at max to end up hitting my sensor. So this 200 now becomes a 60. We ignore all the other sources of noise, and we just think about the shot noise here. Shot noise here is going to be 7.75. It's just the square root of 60. So now if I take these 3 images and I say I'm going to make a luminance out of them, I'm going to average these together and make a luminance, the signal to noise in my luminance then ends up being 13.4. That's how the SNR math here would end up working. Now, let's say I do LRGB and I say, okay, look, I'm just going to do half my time for luminance and half my time for RGB. So out of this 600, 300 seconds goes to luminance and 100 to each of RGB. I'm going to ignore how pretty the color looks right now. In fact, I'm going to throw those frames away when I'm looking at my luminance data. And I see, okay, look, 300, I don't have a filter on this, so all those 300 photons or whatever are going to get recorded. Signal to noise is bigger. Even though I have half as much data, I've thrown away half of my data here. My signal to noise is higher because that filter was letting in more. That signal component in each image was better. If I go to something like 2 to 1, if I allow twice as much time for my luminance here, so this is now, that's 600, I say, okay, look, 400 and 200. All right, again, now my signal to noise is way up at 20. So if I can start short shifting my RGB data here and spend a lot of time in luminance, I can end up boosting my target's SNR a whole bunch. Here's what this looks like in an actual image. Again, this is using my CCD simulator. Here, I have one at, quote, 30 seconds. Now, it's obviously a nice dark site and a nice big scope to have M51 look like that and, you know, one in a 30-second image. But here, I have 60 seconds worth of imaging. So again, it's as if I'm doing a 1-to-1 RGB versus LRGB kind of split here. Here is then what the synthetic luminance sticking the RGB together looks like versus this. Clearly, we're getting a lot more in the arm of M51 here in the luminance image than we are in the RGB image. So digital SLRs and also obviously any one-shot color Astro CCDs can't benefit from this trick that we can pull. And so that's going to end up being one component of why it's tougher to go deep. You're stuck with the provided RGB filters. Now again, I've done lots of one-shot color stuff, and I do really like the convenience of it. In fact, right now I'm actually exploring the idea of having 2 cameras going simultaneously, one doing my luminance and a one-shot color doing my RGB, and that would be pretty cool. You've got more flexibility, all these kinds of things that people traditionally talk about in one-shot color versus RGB. That's one of the components, but it's obviously not the whole thing because I was showing you things like, well, wait a minute here, in comparison to other cameras here, it's still giving you a lower signal-to-noise image, which means you're going to have more data to overcome. Let's talk about the QE. What I'm plotting here, this is actually an estimate of the QE from John Hoot. He did a paper on photometry with digital SLRs. I don't know where he got the various Kodak and Sony sensor data that he was actually plotting there. I actually don't even know where he got this data, to be honest. So I'm replotting it actually on top. This is some data from Apogee's site on the Sony ICX285 chip, looking at its QE. And I've seen this basic QE plot from other people as well. So here we have a digital SLR, and we have a very popular chip used in dedicated Astro CCDs. Now, this is showing a hit. It's not actually probably as big a hit as you really have. This is some data taken from Christian Buell's site, and he is certainly one who has done a phenomenal amount of stuff with and on digital SLRs and getting the best out of them. You can't complain that he's got a bias against them. Here we have the Canon 50D and Canon 40D, 5D Mark II and 5D, and he's looking at the QE, the quantum efficiency plots. So this is how good are you at converting photons into electrons. And what we see is that peak QEs here, so this is 35, 30, here's 35, 30. You're talking roughly 30% as the QE. By way of comparison here, here's the KAF 3200ME. Here you actually have the digital SLRs. So again, you're getting a hit in the QE. Now, I think he's going on a little bit of a rant right now. He's come up with something he calls the geometric quantum efficiency. He says, okay, look, let's look at a little 2x2 grid here and say, what total SNR would I have in this little 2x2 grid? Because, of course, on the one-shot color cameras, you've got a red, two greens, and a blue, but each one of those is only letting about a third of the light through. So in this 2x2 grid, how much luminance SNR do I have? And so he puts it way down even lower there. All right, I'm not necessarily, well, there are pluses and minuses to thinking about it that way. Take home on this, quantum efficiency is lower than that's typically used in a lot of dedicated Astro CCDs. It is. It's something directly related to signal to noise. And it's pretty much acting like your aperture. So what we're going to be getting out of this is just, okay, look, you've got a nice, big, huge honking chip out of your digital SLR. Realize, though, that the quantum efficiency is going to be a bit lower, so you're going to have to do a couple things to try to pull out a better signal to noise in the image. You're going to need to do things like get more signal. All right, let's talk next about this issue here. The read noise is very, very good. It's exceptionally low in terms of RMS read noise here. There are thermal issues, though, that you should be aware about, and this is something I've tried to track down. One of the things that when I first started trying to test these, I have a nice little test protocol, and I say, okay, look, give me a 1 second, a 30 second, a 60 second. I'll just starting to go minutes now, 2 minutes, 5 minutes, 10 minutes. Give me each of these as a dark frame, a little automated script that runs off in Nebulosity to collect these. And I say, okay, let me take a look at the data, and I can plot out and figure out the dark current. And what I saw was that the dark current went down. So let me get this straight. If I take a 1 second exposure, I may have, 500 counts coming out of the camera. And if I take a 5 minute exposure, I have 400. I've exposed for longer and my signal is less. Made me scratch my head and go bald because I scratched my head for so long over it. Here what we're looking at is actually now, this is a sort of dark stability plot. So this is now saying time in minutes. I take 1 minute frames or 30 second frames and I say, all right, what is the mean signal in this? And we see that as the camera warms up and takes more and more pictures, the average signal goes down. Dark current goes up, about doubles every 6 degrees centigrade. So maybe the camera's cooling off as I'm using it. It's possible. This green line is looking at the standard deviation, the variability in the signal. And the variance very nicely goes up as the signal goes up. It has to. It's shot noise. You're always going to have that. You're not going to get around that. The variance is going up, which means really the underlying dark current has gone up as well. And it's just that my readout of it hasn't. Something has gone on. So it's not, I've seen it in almost all of the Canons here. We see the same kind of thing. This is the 5D Mark II. 5D Mark II is the one that I've actually seen that does go up with time. I'm not the only one to have actually seen this. Again, this is Christian Buell's data. This is time 0, and this is 1 hour. And he's saying, okay, look, I'm going to show you the histogram of this dark frame. And you see that as time goes on, the histogram gets broader and broader and shifts to the right more and more. Here is a dark frame at power on. Here is a dark frame after 10 minutes worth of live view. Again, you see clearly, in fact, actually, that noise has to go up. It's not a temperature-controlled camera. But it does mean that this isn't stable. Now, Kevin's going to talk to you a lot about this, so I'm just going to give the very brief overview here, and some of you probably already know. Logic of dark subtraction. All right, we've got some dark current coming in. It's going to be in our light frames. It's going to be contaminating our light frames. Each pixel's got to have a different amount of sort of rate of dark current buildup. If we can take an image of that, because we know we have a 1 minute light, if we can take an image with a 1 minute dark, we can subtract that out. The noise component we can't pull out, but at least that variability from pixel to pixel and the total dark current we can subtract out of our image. That's only going to work if you can actually estimate that. If you can repeat in a dark frame that which you had in a light frame. Now, since there's noise associated with this, we take whole big stacks so we can average out that noise and get a really good expected value of the dark current so we can subtract that out. Problem on the Canons right now is that there's a sort of a doubly moving target that you're trying to subtract. One move you all can already sort of guess because, okay, look, we know that the temperature of the sensor varies significantly while imaging. This is move number one. So some people do things like try to take their darks during the capture as well to let their darks track and go along with the light frames. It's a fine solution to that problem. Dark current is significant in the cameras, so okay, we can subtract this out. Move number two, though, is that there is an image scaling that's going on. And this is then going to be something that's going to make it a little tougher. There's an actual scaling of the data that's going to make things like dark subtraction or even bias subtraction tougher because that dark current and that bias current is getting scaled by something that you don't really know about. So it has nothing to do to help the noise. It does make, in many ways, it helps with quantization. And this is one reason I believe why Canon's doing it. It makes very, very good sense for a daytime kind of, or nighttime, standard kind of photography sort of shot. What they're going to do is they're going to pull this histogram out. They only have 12 or 14 bits to stick the sensor data in any case. So let's actually just take out a lot of this for you. In many ways, it makes good sense, but it does make our lives as astrophotographers a bit tougher. Here, I'm showing you the histograms of some dark frames. We have a 1 minute dark in blue, a 5 minute dark in red, and a 10 minute dark, a 5 minute in green and a 10 minute in red. And what you can see here, this is on this 350 XT, the histogram actually moves to the left. This is the, I'm shooting for longer, but my image is getting dimmer phenomenon. You do also see, though, that of course the distribution gets wider. Wider thing, because there's more thermal noise in there, we should get a broader distribution. Not all of them do this. I, in fact, think that this shift to the left is due to the glow in the 350 XT. I think it's using the optical black as a way of actually figuring out this calibration here. The 4DD shows a very, very little in the way of shift, but it should be, if you're getting a wider distribution here, it should be shifting to the right each time. If you have a very thin distribution, like on a cooled camera, well, it can basically stay where it is. Okay. Actually move forward here. Now I'm telling you that there's scaling going on, and I've shown you some evidence for it in the fact that the image is getting dimmer despite the longer exposure here. Here's what we have. Here's sort of actually showing that, showing the actual dark current plot as a function of duration worth of exposure. And as far as I know, there is no way if you have photons coming in at a certain flux, worth of dark current coming in, that if you go longer, you are going to have fewer photons. I just can't sort of make that make sense in my head. Again, I've shown things like the variance is going up, which is saying that yes, in fact, really, there are more coming in. It's just that something is going on to make the signal itself go down. Now, I've also been able to look at this. There's a prediction that I made for one of the reviews to say that what we should see is actually a change in the contrast. And I've got some data to suggest that, yes, in fact, actually, there is a shift in the contrast, as if they're basically stretching the image a bit to then take out this overall mean shift up because of the, I'm not sure that's entirely it. I'm still not exactly certain the equation that they're applying to the image, but it's clear that something is going on to the image. And if that something that goes on to the image is different in your lights than your darks because they're at a different temperature, or you're going to say, okay, look, I'm just going to do bias frames and just pull out these lines because of the bias, well, as you take all of your bias frames, ka-ching, 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 your sensor starts heating up, which means that those bias frames are going to get stretched as well, which means then that that's not actually a good reflection of the bias current, which means that the logic of the subtraction falls. Yeah?
Are you doing that in raw mode?
Yes, absolute total raw mode. I even don't let Canon do the debayering. I just get the raw sensor data off myself. Yep, good question. Now some will think, okay, look, let's just use the onboard dark current subtraction by taking a dark frame after each light frame. All right, that's going to help with this temperature tracking issue and presumably some of the scaling issue that goes along with that, but you're now using just one dark frame. And that dark frame, remember, you got that shot noise from the dark current, and it's an appreciable signal. You have one sample of that instead of 50. So all the variability in that, because no two dark frames next to each other look exactly alike, you're subtracting out something that probably isn't in your light frame because it's just a noise component. So you're injecting noise into the image. You're taking some out, but you're injecting others in. So it's not going to be a absolute cure-all for you. All right, so we've talked about the internal scaling and about the thermal issues associated there. Fixed frequency variable location noise. What I'm showing you right here, this is a bias frame. I could have done it from Kevin's cameras as well, but I kind of figured I should give somebody else some credit here too. And also say, okay, look, let's just not pick a $5,000 camera for everything I do here. This is the ATIC 16IC. All right, much less expensive kind of camera. This is a bias frame from it. And what I'm going to do now is I'm going to now show you the very next bias frame I took in the series. Well, one thing that you can look in here, this looks like, I mean, fortunately, when I talk to students these days, I can't ever give the analogy of static on a TV screen because to them it's like, well, when there's no signal, it's blue. Yes. To this crowd, remember static on a TV screen? This looks just like that. And that's great because that's a nice sort of Gaussian noise. Here's the next one. This is just noise. There aren't any like bizarre artifacts in here, and it looks like pretty nice, good noise. I'm showing you next up here now. This is from Canon XSI, and as I say, I've tested a bunch, and they all really show the same sort of setup to varying degrees. Take a look here, however, and what you should start to pick out is take a look at these horizontal streaks. You can also actually pick out there are some vertical streaks as well. Now what I'm going to do is I'm going to show you the next bias frame. Oh, yeah, look at that. So what you can see here is that actually the vertical streaks are actually pretty good at maintaining their location right here. And I can't seem to manage to.
Yeah, I see what you're saying.
But the horizontal ones, let me try to be a little less spastic here. Okay. The horizontal ones, of course, are moving. All right. So what's the right thing I should pull out of the image? My image of M51 has this in it. My dark or my bias has this image. So when I do a subtraction, I'm not actually subtracting those. The best I can hope for is to have enough frames to let that all wash away. And that's a very, very good trick. When you have something like this that is a variable location kind of thing, what you're going to need to do is you're going to need to then have enough to let that location kind of hit everywhere. So your shot where you're going to say, okay, look, here's what I'm going to do. I'm going to take 4 15-minute shots. Well, okay, yeah, you're going to end up, okay, you've got to be in the Arctic to do this because the thermal noise, but let's say that you did that, you're still then going to have this in here, and you're going to need to somehow pull that out. You might be a lot better saying, okay, look, let me turn these into 1-minute subs so I can let these things average out a whole bunch over frames, at least as best as I can. We can actually try to quantify this and not just look at it visually with something called an FFT, or a fast Fourier transform. What I'm showing you here, we have the average row and the average column from 2 cameras. This is the QSI 520 I reviewed for Al, and this is the ST2000 that I owned at the time that was also in that same review for Al. And what we can see here is we're looking at the average, the sort of fixed horizontal noise versus the fixed vertical noise. So how does it change as you move from top to bottom in the image is this. And what you see is that there's a little bit going on here as you move from top to bottom. As you read out these sensors, you end up seeing that, okay, look, there's a little bit of a buildup of charge in the register. And so the top is always a little bit dimmer than the bottom. You always get this. It's very nice and very repeatable. And you see it in a ton of cameras and a ton of sensors. Going the other way, across the image, it's got nothing. That's really good. All right, we take a look in something like the ST2K here. And what you see is, you know, this way it looks similar. This way here, there's more stuff in here. This actually comes from the hot pixels on the S-Big, show little streaks that come down. And they're always there, and so they're repeatable, and so you can pull them out. Here, however, is on the same scale what two of the Canons look like. There's clear structured noise going on here. And this is frequency in the image, so how sort of repeatable, how wide a distance between these things. What this is really just showing is that there's a whole bunch of different stuff, different lines going on here in the image. We can see there are a couple of things that are very hot spots, which means that this is going to be some sort of very clear demarcation in the image at these frequencies. What I'm showing you here now are two-dimensional FFT plots. So instead of looking at an average line or an average column here, now this is in the image itself what frequencies are in there. So you can get all sorts of things where if you have like odd diagonal things going through the image, you can end up picking up this kind of thing very nicely. The ideal thing, if I were just in MATLAB to say here like, okay, create some image, give it an offset of 1,000, and add 8 ADU worth of just random Gaussian noise, would be that there would be a bright dot in the center and there'd be just kind of noise around here. And that'd be it. If there's some structure in this, there's some rippling kind of thing in this, what you're going to end up seeing is that, well, bands that are vertical are going to end up being horizontal lines in this 2D FFT plot. And so we see on the QSI here, that's really good. On the ST2000, that's good. There's a little bit of something in here. Me DSi 3 Pro. Okay, you can start to pick out there's a bit of a line right here, and it turns out there's a little spot. You can always check in these FFT plots. There should be something in the exact opposite. So there's a little thing here. There's a little bit of a frequency. Q8, overall the noise is higher than here, but there's not too much structure going on here. There's a little bit. You can start to pick out there's a little line here, a little brightening in line here, brightening in line here. But we see that there's more structure in the frequency domain in these other cameras. Now, if it's always fixed and it's always repeatable, you can subtract a lot of that away and at least make it disappear. It's still going to have noise associated with it and that you've got to deal with, but you can at least try to pull a lot of it out. If it's not fixed and it's variable, well, then you're going to have it build up in your image and not be able to subtract it. Here's a really, really bad shot of an M31 taken in an urban location. I can say it's really bad and I can insult the person who took it because it was me. What you should see in here are these vertical lines in the image. All right, there weren't a ton of things that went into this stack, and so I'm still seeing some of this stuff in here. So what this means is that I'm going to have to do more work to pull out the image and get something that's clean. Now this is on an older one. Again, this is the 350 XT, and there certainly have been advancements that have been made. But in one of the comparisons, I was comparing against pretty darn current Canons. All right. Take-home message number 4, there's horizontal and vertical banding in the images. Locations of the bands and streaks can vary from frame to frame, in particular in the horizontal streaks there. So therefore, you can't remove them by subtraction, and you're going to have to let them average out or be low enough in your image that you can kind of clip them out, which means then that your target's going to have to be that much brighter in there to be able to say, okay, look, I got some noise down here. Let me cut that off. All right, it means that you have to have worked to get the target there that much brighter, or you're on a brighter target, which is why I phrase this as not, oh, they can't make pretty. Of course they can make pretty pictures. I've seen some stunningly beautiful pictures off of digital SLRs. It's why is it then when you decide I really want to go after these able galaxies that you're going to have a much tougher time? And that's what I'm trying to get at here. So variable location pattern noise will come out as you stretch it, and this is not something that's really all that common in dedicated Astro CCDs. All right, so I want to leave you with a couple of bits of overall summary here. There's a phrase, garbage in, garbage out. Okay, that's obviously being harsh in this case because these aren't garbage, but it's a notion of, all right, if you're going to, the higher quality you have going in, the higher quality under the same sort of circumstances you'll have coming out. But that's not as fun as saying GIGO, and so people call it garbage in, garbage out. Targets SNR is what we really actually care about, not just some raw SNR in the frame. I don't care how great the SNR is in a star is. I can have great SNR in a star with my Philips, old 690 Vesta webcam. What I care about is in that galaxy, in that nebula. What is my SNR actually there? Your camera and your local conditions are going to really sort of conspire to both give you the overall SNR in your images here. In addition to SNR, I mean, it's not just that noise is noise, as we can see, like in particular, say in that shot of M31 there, our eye is going to be drawn to things like streaks. I'm a cognitive psychologist by training, and so we think about Gestalt rules, and your eye is phenomenally well tuned to pick out lines. Digital SLRs have a number of relevant issues that's going to make it a little bit tougher for them to end up really going as deep. You've got the sensor QE, you've got the thermal issues, and you've got things like the scaling tied in with those thermal issues and the fixed pattern noise. All right. Take-home message as to what to choose. I said in the beginning that there are a lot of different constraints that we're all going to be working under and a lot of different trade-offs that we have to face. If you have 2 cameras sitting on the shelf, or you have 25 cameras sitting on the shelf, and you've got, an Astro CCD that's got a big enough chip for the framing you want to have, grab the dedicated Astro CCD. They're both sitting there, and that one's probably going to have a higher signal-to-noise for you. All right. Both sitting on the shelf, but the Astro CCD is way too small. You really want M31, you want the Pleiades, and you have, a sensor this big, and you also have a digital SLR. Yeah, grab the digital SLR. Don't be an idiot. In terms of your overall signal to noise here, I mean, I'm saying, oh yeah, you're getting a better signal to noise in the luminance channel and everything, and look, yeah, the Canons are, they're behind. If you have to do a, 81 panel montage, how good do you think the signal to noise is in any one of those panels? Not very good. All right, because you have 81 times more data from the big chip because it was there the whole frickin' time. Obviously, grab the big chip digital SLR. New purchase. Mainly like shooting galaxies and little planetary nebulae, and you want to say things like, oh yeah, H alpha is going to be something I want to do or something like that. Well, okay, look, this is pushing you then more toward a dedicated Astro CCD. You've got a fixed budget and you need a good daytime camera. Kevin's cameras can do a lot of things for you. They are not good for vacation shots. Grab a digital SLR. If you want to be able to, though, go as deep as you possibly can on something, and that's really where your sort of passion in this is, well, you're going to get a higher signal to noise out of the dedicated Astro CCDs writ large. Any individual comparison, of course, these are overlapping kinds of things. There will be dedicated Astro CCDs, and I've tested some number of them, that will not be as good, and I would definitely grab my Canon off the shelf instead of that one to go out with. But on average here, I hope I've tried to show you why it is that you've got a little bit higher mountain to climb when you're using a digital SLR instead of a dedicated CCD. So with that, I'd like to conclude, and thank you very much for your time.